I think we should be live. Let's just check this out. Okay, cool. Hey, everybody. So today I wanted to spend some time on Pyjion, which is this JIT compiler for Python that I've been working on. And there's a talk coming up at PyCon US 2021, which is in 2 weeks' time. And I've recorded my talk for that already, but I'm going to go through the JIT compiler and stuff like that, and the project and generally how it works. This morning, actually, I was just thinking about the particular problem, and I was thinking of just experimenting with trying to optimize the compiler to deal with some situations related to comparisons. And I thought maybe I'll just record that and just do a live stream while I'm working on the problem. Some people might find it interesting, or you might just have questions, or you might learn something from this. So hopefully I'll explain things as we go, and hopefully you can learn something from what's going on. First things first, let's start off with this file, because this is the benchmark that I'm using to compare improvements in performance. This isn't a benchmark that I've written, it's one that's used in the PyPerformance project. And I don't know where it originally came from, but we'll just talk through, I guess, exactly what's happening in here. So this is a pure Python file, and I'm executing this in CPython 3.9 and then measuring how fast it runs this code, and then enabling Pyjion, the JIT compiler that I'm working on, in these two lines, and then running the benchmark a second time and then comparing, what the timing is and stuff like that. This benchmark's also useful because I can run this as a profiler. So the key, I guess, is I'm trying to see what's making this benchmark slow in CPython, and then what can Pyjion do to make that faster. So let's just talk through, I guess, the benchmark itself, and then we can work on what's happening here. So we've got a class that's been defined pure Python. It's using dunder slots, which are an efficiency mechanism actually that's built into Python. You can define a tuple in the class of properties that are often accessed, whether they're being set or read. And in this case, point will have some properties X, Y, and Z. So dunder slots is equivalent, I guess, of doing X equals none, Y equals none. And then you kind of specified up front that you've got these three attributes, and they'll probably be assigned in the constructor. However, dunder slots is actually more efficient than that, because what it does is when it designs the class object in the Python compiler, it actually allocates the space for these up front, which is much more efficient. So adding a slots to any class, if the fields are static, is a great efficiency tool. The next thing we've kind of got going on in here is the initializers. So we've got X is being assigned to the sine of I, Y is being assigned to the cosine of I multiplied by 3, and then Z is being assigned to the square of X halved. Not entirely sure why. I think they're just three interesting numbers, and that's why they're being assigned that way. I don't know if there's an equation maybe this is based upon. But yeah, I think these are just they're dynamic numbers, so you can't optimize this just by predicting the results or caching them or interning them or anything. The dunder repr method just prints out X, Y, and Z as the attributes. Normalize will... Okay, what's going on here? So we've got X, Y, and Z. Okay, I think this is just a calculation that is floating point heavy, and I think the goal is to have something that does a lot of math with floating point numbers, similar to what the n-body algorithm does, which is something that I've been focused on with this project. So here we're doing an in-place division operator, we've got multiplications, addition, and then passing that through to the square root function, which should be in the math module in the standard library. So that's interesting. And then we've got maximize here, which, what is this doing? So this is a ternary operator in Python. I always find the syntax weird, but assign self.x to x if x is bigger than the other x, otherwise assign to the other x. So I guess it will return the highest x, y, and z of when you're comparing self and other. So if you're comparing 2 points, then it will basically do the larger of the two. I think that's right. Yeah, the larger for the x, the y, and the z. And then we've got a function here which does, given a number of points, it will start at the beginning and then work through each one and maximize them. So I think what it's doing is essentially generating a number of points. In this case, it's 100,000 point instances. It's assigning x, y, and z of those to sine, a cosine, and a square divided. And each time I believe I is incremented because it is assigned from a range iterator, which is from n, which comes from the number of points. Okay, so what this benchmark should do is essentially create 100,000 point instances and then calculate which is the maximum point which is generated by normalizing the points and also doing a maximize operation. So okay, so given a list of points, it will find the greatest set of coordinates of x, y, and z. Okay, that makes sense. So I haven't actually looked at the code much for this. I've just run the benchmark because I know it's one of the key benchmarks. So so in this operation, if I run that with just CPython, then it's relatively fast. If I run it with Pyjion, then it's slightly faster. In this case, it's about 10% faster. I think the last time I checked, I was working towards 15%. The reasons why it was faster, these three operations here are more efficient in Pyjion because, no, this operation is more efficient in Pyjion. I think that's the only one really that I've actually optimized, is where you have a series of what are called binary operations like multiply, plus, divide, minus, where you have a series of them. The carryover number will be kept as a C float rather than being converted back into a Python number. So I think it's getting 10% performance improvement just because of that one optimization. There's nothing else groundbreaking happening in here. What I can do in C-line actually is run this as a profile, which I haven't done for a while, but we'll see what happens. Okay, now this is running in debug mode, which means the Pyjion is going to be a lot slower anyway, because it's doing a lot of extra stuff that CPython isn't doing, because I'm running CPython in a release compilation version, whereas Pyjion, is being run in the debug mode, so it will be slower. I expect that absolutely, because in debug mode it does a ton of extra work, and also the C compiler, C++ compiler for Pyjion will be compiling in debug mode as well, which turns off all optimizations. It does that because when we run a profile like that, we want to see this information. So let's make this bigger because it's pretty tiny. And maybe we'll step through some of what's happening here. So each one of these, I guess, like little mountains. So this is the call stack, and what you'll see is that will come from if it's got a number like this, which is just a memory address in this case, that is actually a JIT compiled function. So it doesn't know the name. That is really tiny, isn't it? Is there any way to make that bigger? No, I don't think there is. I'm just going to have to describe what's happening. Okay, so each of these, I guess, sort of mountains on this graph will be a call. And as you go further upwards, it then calls different functions. So this is a profile of both Python and C calls. So because CPython is based on, is written in C, then this will heavily be using, C calls, and that's what it's profiling. So this stack here on the right-hand side is the CPython call stack for this benchmark. The version on the left-hand side, so this area here, is the Pyjion one. So I know that because it's doing, I can see Pyjion being used here, and it's that is a JIT compiled function. That function probably is the entry point, which is the benchmark function. So the benchmark function will be JIT compiled, and that is probably that memory address there. Then we've got some method calls, which would be, what have we got? P and p.normalize. So that's the normalized method calls. I believe, is that right? I think next.maximize p, that's got two arguments. One is self, which is next, and the other is p. So there should be a method call 2, which I think is this one. And then eventually it's breaking up into different stacks depending on what's happening here. So a lot of this is floating point numbers, which is what I'm interested in. So if I zoom into that stack, we've got float division going on. Actually, let me put this as a tree because it's easier to look at the call list. Where's it gone? Let's just scoped it out. Try and find the one I'm looking for. It is called float rich compare. Where is it? It's hiding in here somewhere. Okay, so let me point out the line. So this line here that says x if x is greater than other x, otherwise this one. This is the one I want to optimize because it's not super efficient in Python at the moment. The way that this works, let me just pull up a REPL. Make that bigger. So if we did a number, so x equals 1, y equals 2.5, I guess, and you return x is greater than y. So you would expect that when you run that function, it's going to return false because x is smaller than y in this case. So what actually happens with the CPython compilation for this is that it will compile that down to an operation called compare op. And the number here on the right-hand side, 4, is just a enumeration of this symbol. So this is the greater than symbol, yeah. So it's saying, is x greater than y? Compare op takes 2 inputs. It takes, in this case, the left-hand side and the right-hand side of the operation, which is the variable x and the variable y. They're coming from load fast because I've specified them up front. If I didn't do that, if they were coming from maybe an argument or, no, not even an argument, maybe a different function or somewhere else, that would be load name instead. If they were global, that would be load global. So compare op basically just is a generic comparison operator for any two variables. And you would do that if it was equal equal, if it was less than equal. There's actually a whole range of them. This was introduced quite a long time ago. I'm not sure how long ago actually. The rich comparison PEP basically is the specification for this. I'll have to find the PEP number and put it in the notes for this. But so the rich comparison PEP basically says that it will always compile it down to the compare op, because you could make a custom class for X and you could define your own less than by using dunder.lt. You could do not equal to by using dunder.ne. So you could basically implement the magic methods on your own types and get a lot of control over what would otherwise be like operator overloading in other languages. So the way that you do operator overloading in Python is you make custom classes, and in the classes you implement these dunder methods to define the behavior of all these comparison operators. Now, my idea is that Pyjion knows that X is a float and Y is a float because I've just defined them. So it should be able to say, okay, instead of using the generic compare op, why don't we just load the floating point value of X and the floating point value of Y, and then do a low level comparison. To see how that's done in CPython, let me bring up the CPython source code. It's going to take a while to load that up, but the code you're looking for, if you want to check this out, is in the CPython source code. There's a folder called objects that has the definition of all the built-in types. So we're going to look at float object because that's the one that I've been fascinated with for the last year. Also, if you want to learn more about rich comparisons, in my book, in CPython internals, we actually add a whole new comparison operator called almost equals. So we actually implement this from scratch. So you could do X almost equals Y, and you could say X equals 1.01, Y equals 1.00, and X more or less equals is almost equals is what we call it. That would actually evaluate successfully, and you can define that as, we also did like case insensitive string comparisons as well. So you know, you could do hello almost equals to hello. So if you're interested in digging more into the grammar of this, and also I guess customizing CPython, then check out the book because I walk through from scratch how to implement that feature. Okay, so once this is loaded, we should have, no, it's not loaded the symbol yet, but I know where it is, so we'll go and bring it up. Okay, so when you do a rich comparison, it will look up the, it's a bit complicated, it looks up the left-hand type to see, so it looks up the left-hand type first, so it defines basically a rich comparison implementation using something called type slots. So built into CPython is this concept of type slots where all of the C implementations of types will define a structure, and they say, this is how I implement creating a new instance, this is how I implement doing addition, this is how I implement doing, you know, any number of operations, slicing, indexing, multiplication, pretty much everything you can do in Python, like at its low level, is defined in a type slot, other than obviously things like methods, like custom methods. So this is how CPython is optimized internally, and for rich comparisons, there should be a generic method for each type for rich compare, and it would take two inputs. It would take the left-hand side variable, which in this case is called v, and the right-hand side variable, which is w. And then it also takes an integer, which is the actual operation itself, which in the quick function I showed was the number 4, which represented the greater than. I think we'll probably see that referenced in a second. This is a big function. So, okay, here it is. So pi equals is 2, not equals is 3, less than equals is 1, greater than equals is 5, less than is 0, and greater than is 4. So that's the one I was looking for. Okay, cool. So what is interesting is what will happen here is this function will get called with the numbers that we defined, which were 1.0 and 2.5. That will be called with the number 4. At this point, v is a Python object and w is a Python object. This function returns a Python object. That is challenging because what it actually does is it returns a number, and then the thing that's calling this, which would be this is the type slot that I was talking about. So this is tprichcompare, which should be in one of the abstract classes. Let me just find it. Pi object compare. That's the thing I was looking for. So this is the entry point. So if you ever want to compare two objects at a C level, you'd call pi object rich compare. That's the function that's called from the compare op. This is the evaluation loop, by the way. This is the thing that gets looped over for every opcode when you execute a function. And it's saying, okay, the right hand side is on the top of the stack, the left hand side is the second variable down, and then run pi object rich compare with left and right as v and w. It will then look up for v. This function basically says, does v have the rich compare type slot implemented? If it does, then call it with, is it the right way around? I always find this confusing because if it, no, that's the right one. If it does have it implemented, call it with v on the left and w on the right. If it doesn't, if the type doesn't have it implemented, but the other one does, then it calls it this way around. So what I mean is, if you're comparing x on the left and y on the right, but x was a custom class that you defined that doesn't have a less than or equal to or not equal to slot, like you haven't actually put the magic method in, but the right hand type does, it will call the right hand side. And it works that out by saying, doing this swapped operator. So if you're saying left is left less than right, but the implementation is only available on right, it will call the right hand side but with the opposite operation, which is done in this kind of funky like list. So what is the opposite of less than? It's greater than. So that's kind of how this works internally. It's a bit confusing, but it looks up the type slot and then it will call the function. What it then does is return result. Which, let me just remember where it does this. Because it should eventually return a boolean of either true or false. True and false are special in Python because they are interned values. It doesn't actually generate even though true is a Boolean object, they're recycled. So pi true is a recycled version of the true object, and pi false is a recycled value. Otherwise, it would just use a ridiculous amount of memory, allocating and deallocating Boolean values, which is completely pointless because they're not going to change. So I think the last thing it will do is where does it go? This is where I get confused. Okay, it's called the type slot. It's calculated the answer, and then it returns the response. Now, we were looking at the implementation for float objects, which was float rich compare. It will basically try and convert V to a double and W to a double. It then does that and calls them I and J. And then it does the comparison at a C level, which when CPython is compiled, that then compiles down into machine code instructions to say compare these two memory addresses as floating point numbers, which any CPU can do super efficiently. My theory, I guess, is that there's a lot of stuff going on before it gets to that point. So if I know that V is a float and W is a float, then surely I could compile that down in the JIT to be a much simpler comparison and then yield the true or the false interned objects rather than doing all this extra stuff. Because inside this function it says, okay, first of all, just if V isn't a float, then crash CPython, because that shouldn't even be called in the first place. That cert should never fire. But first thing it will do is convert a pi float to a double. This is actually a macro because in the float object there is a field called ob_f val, which is the double. Where is it? It's at the top. Here. So this is what a float object looks like in memory. It's got the pi object head, which includes reference count and the type, and then it just has a double, which is the value. So float objects in Python are actually very, very simple. In the implementation, they're just a double with a Python object wrapped around it. So what that macro will do is just extract the double value out of V. And then if the right-hand side function is a float, which it can assert by running pyfloat check, then extract J to be, again, from that field. So in our case, both of these two things are true. So I should be 1.0 and J should be 2.5. So then the code would skip down to here. And then we've got, okay, what happens next? So the compare operation, which was the number 4, which was greater than. So R equals I greater than J. When you, this is the weird thing. So if you do this, then what it will do is basically it will run at a C level, compare I and J, and then the result will be R. Now you might be thinking, well, what is R? So R is an int, but it's either going to be 1 or 0, I believe, because it's doing booleans and integers in part. Okay, so confusingly, booleans in Python actually inherit from longs, but what it does is it converts either the number 0 or 1 back into a bool. Pybool from long is, as you'd expect, very simple, which is just says, if it's 1, return true, if otherwise return false, and increment the true or the false objects. So that's actually pretty efficient, the object. That's not too big an issue, but it will return true if I is greater than j, and it will return false if it isn't. So that's kind of how the float comparisons work. I guess what I wanted to optimize was how that could be JIT compiled, because I think Pyjion can be a lot smarter than this. Not smarter, I mean, it's generic, but it's not efficient. So if we go into Pyjion, I guess there's a few things we can kind of want to show you before I kind of get stuck into this, but the interpreter is the thing that I guess manages the compilation of there's basically two stages where this will come up. There's this phase, which is the initial phase, which is basically being used to assert what types things are, and that is then used later in the stack. So Pyjion basically has like an abstract value stack that's used at compilation time, which is used to optimize certain things. So for example, if I know that the build map operation always returns a dictionary, then push onto this abstract stack dictionary type. Compare op could return anything, I believe, because technically it doesn't have to return a Boolean at all. Like you could implement a magic method that returns a string. I don't know why you would, but you could. So it just pushes any type. The second phase of this is where we do the comparison operations. This is actually the compilation part. So there is one optimization already that I've done, which I believe, let me try and remember where that is. So compare known objects. Compare objects. So when the compiler runs, what this code will do is it emits. It doesn't call because it's compiling. It should just emit the instructions onto the compiled function, and then once all the instructions have been emitted for this code object, then it will basically compile that down to machine code. So it either does this one or it does this one, depending on whether this optimization called intern rich compare is enabled. So Pyjion has got, anytime I write a new optimization, I define it in a CMake profile, and I give them all names, and then they're all numbered and documented. So intern compare was a really early one that I worked on, and it was to do with comparisons of interned values, which are the numbers -5 to 200 and something, and true and false, I guess, as well, like would be another example. So I do actually have an optimization for this already, but it's pretty basic, and I'll show you that in a second. But I guess what I have to think about is that I've already got one here. So do I have to write another implementation or stick with this one? I'll work that out in a second. So this optimization can be turned on and off at when you use Pyjion by using this method here called set optimization level. That will set the optimization profile for the JIT compiler, and each of these optimizations I've grouped them into, they have a like default level. Let me find it. It's in here somewhere. Here it is. So when you run that, it will turn on and off different optimizations depending on the level. Pretty much all of them are at level 1, apart from this one called native locals, which is buggy as ever. So I put it into level 2 because sometimes it works, sometimes it doesn't, and it does give a performance improvement, but it might also just explode. Okay, so this is what we're going to do when we do the comparison operator. I'll show you the generic version first because that's, I guess, the simple. So this is the generic one. it is very simple. So all it does is it will ML is our ECMA is still compiler that's been written for Pyjion. This is something that I think Dino originally wrote, but it's kind of been extended over the last year or so. So load a 32-bit integer onto the value stack. That's what that means. And then emit a C call to a token called method rich comparisons, which I defined in here as calling a function called Pyjion rich compare. So when that's actually compiled, all that will do is the machine code instructions will just say call this function. So like it knows the address of this symbol for this function, and it just calls that function. That is literally all it does. So it just completely imitates the C Python implementation of this, the one I showed you here. So this is doing exactly the same thing, which is call this API, decrement left and decrement right, and return whatever the result is. There's no optimizations there at all. That will run at exactly the same speed as C Python because it's doing the same thing. There's nothing fancy going on. The optimization I was mentioning before is in is this one, and all this does is it says if the left hand side is an interned value, which like I said will either be true or false, like the Boolean values, or it's a number that's between a constant number that's between -5 and 255. It's unlikely that this optimization is hit because it's quite unusual, but all I'm essentially doing here is saying like x equals 11, y equals, I don't know, a big number. Is x equal to y? So all this is doing is saying, you know what, in C Python, all the small numbers, so between -5 and 250, I think it's about 256 or something, those numbers are not created each time they're referenced because they're used so often. So what it actually does is when you start C Python, it will actually create what they call small integers and put them in like a cache. So whenever you use the number 11 in future, it will actually refer to the same object. So small integers in Python are like an internal optimization that's used in C Python. And what I'm doing here is I'm actually just leveraging that optimization to be a bit more efficient. So if it's saying, if this is the equals comparison, then actually just do an is operation. So what this basically says is if the left-hand side or the right-hand side is a small number and it's a constant value, which it is, I mean, that will be 11 because I've just told it it's 11. It would essentially run x is y instead of x equals y because that is a much more efficient way of doing that comparison. That's all that optimization does. It's unusual that it would get called because it assumes that you've got a constant value. If you did Booleans, it would warn you in the first place. So is that true? No. If I can't remember how you do it now, but Python does actually say as a warning, it emits a warning saying if you're doing is, if you do equals instead of is for Booleans, it does actually say, are you sure you meant to do that? That's not particularly efficient. And then if either of those cases don't eventuate to anything, it will then call the generic method. So that's the theory. So I guess what I want to do next is then say, can we write a more efficient comparison operator for some types? And I wanted to start off with floating point numbers because I've got two benchmarks that I've been pursuing for floats. It would also be nice to do it for strings because equals a not equals for strings is used so heavily. However, the implementation for that is really complicated because they're Unicode objects, and Unicode comparisons are like crazy complicated. Let me see if I can find it because it's I don't even know what that implementation is. No. Unicode rich compare. This is a complicated one. I mean, it has a shortcut to say like if they're actually the same object, then like that's one shortcut. But otherwise, it runs either compare equals or compare, and then this is where it gets nuts. So because you've got different byte kinds, you've got different lengths, Unicode, different encodings. Oh, it's just a nightmare. So the thought of optimizing this gives me chills. So floating points seem a lot easier, to be honest, because I just need to do this. Like, can we compare I and J? So yeah, what I was thinking is something really, really, really simple, which is, can I just do like literally if the left-hand side, I think is known, which means in the abstract stack, do I know what the type of the left-hand side is? And do I know what the type of the right-hand side? Actually, let me do something else first. I also need to do has value, I think it is. Forget my own API. Okay, something I could optimization for binary operations like plus and minus and things like that, but it doesn't. Plus and minus is a bit different, and I don't think it does. It adds a bit of performance gain, but not a huge amount, because the result has to be a new object anyway. But in this case, because the result is either a true or false, which is an internal value, then it's very efficient to emit that from machine code. So what I would do for this optimization is probably just switch the left hand side type, which and then I know that I'll have an implementation for floating point numbers, and then I'll just probably return back from this because I don't need anything else. And then just implement this one. So however, I also need to check on the value of the right hand side, because if that is an integer, then that's going to be a complete different set of instructions. And integers are much more complicated to extract. So what I'll probably do is just, this is a bit gross, but I'll rewrite this in the future. Okay, if the right hand side is a float as well, then do this, otherwise just break out there. Okay, now I don't have emit compare floats defined yet, but I'll do that in a second. I will floats. And I'll put it just above this one, so I can actually put it just here, so I can just see what's going on. Okay, so what this now needs to do is emit the machine code to compare the left and right values depending on which comparison is done. Now, probably the right way to do that would be to switch the compare type and then emit the code for this. This might end up being quite a lot, but I'm just going to give an example of greater than. Because I think there'll be quite a lot of stuff happening here. I might eventually just move this out into its own source file, but left. My CPU is melting. Why is Docker using my CPU? I closed it. All of my cores are running at like 100%, so. Okay, stop compiling, that's good. Okay, so greater than, so we have two values, I guess, on the stack at this point. In the SIL, there's a couple of ways you can use the stack values. Because, let me just think how this might work. We just double check my thinking's right. So the top of the stack is the right hand side, and then the second value down is the left. So what you can do here is you could the SIL. So we're using the Docker compiler, which uses ECMASIL, which is a standard that was created as an intermediary language between .NET's common language runtime and the machine code that's emitted, because the common language runtime should emit for different CPU architectures, and now it even supports different operating systems, like .NET 5, which is what this is using, will work on Mac, it works on Linux, it works on Windows, it works on ARM, it works on x86, 64. So there's basically an intermediary language between the JIT compiler and the actual machine code. I have got a copy of the documentation, which I use for reference quite often. And I'll show you, don't care. GitHub loves to ask me that, like really, really often. Okay, so there is a branch operation which is called that's BGT. BGT, is it? So in the ECMASIL, the operation I'm looking for is branch greater than. So it would take a value 1 and a value 2, which you need to think about, I guess, the stack values and how the stack order and the stack values, just to make sure I didn't end up accidentally getting this the wrong way around. And when you do a greater than, it actually does the opposite. But what it will do is it will run a branch operation if value 1 is greater than value 2. So if that's the stack, then value 2 is the top and value 1 is the second. So in our case, let me just, this is going to confuse me. But also this would only work for like native types. And at the moment, it's a Py object. Like it's got no idea what to do with that. So what we need to do is actually replace the Py objects on the stack with the floating point numbers, which are the doubles. So I know that we know what the field is. So what we can do is basically I don't want my lint. So the SIL also has not only it has a value stack, as you'd expect, but it also has the concept of numbered locals. So you can basically it makes it a lot easier to work with these sort of locals. In the compiler in Pyjion, you can just define them, and then for example, if I wanted to save the top of the stack, let me try I get this the right around. Okay, the top of the stack is right. So let's actually get that right. So if I wanted to save the top of the stack to the right, then I would do emit store local, right? And that would emit the operation to store the top stack value onto right. And then I could do emit store local left. And it would store the second value on the stack to left. It not only it pops it as well. So now both of my values have been popped off the stack and they've been assigned into a local variable. The JIT compiler is pretty smart. Like it won't allocate it doesn't allocate the memory. It has a heap to do it, but it will either put that address in the heap, or actually, that's not a float, is it? It's a pointer at this point. Sorry, because it's a Py object. So it will, in some cases, it actually uses registers to do this. So it can be pretty efficient. From what I've seen, anyway, in the assembly, like it has a registry allocator and a register allocator, not a registry allocator. It has a register allocator, so it can use CPU registers for this operation. So you don't have to worry too much about that, adding performance overheads to do it. So let's store the right-hand side and store the left-hand side. Now the next thing we need to do is extract the floating point numbers. So we could do this inline, which probably makes more sense. However, when we're finished, we're going to need to decrement the right-hand object because if you go back to here, it decrements left at the end, and decref basically decrements the object ref count field on the Py object pointer. So I could, like, instead of storing that, I could just extract the floating point number and then store it, but I would have popped the value off the stack, and then I can't retrieve that back again to then decrement that object. So the last thing we'll do is decrement, and just for sanity, I'll put them in the same order. So that I know the last thing I want to emit is load local, and I also want to free it because I'll never refer to it ever again. And then I'm going to omit the decrement. Decref in Pyjion is actually very efficient. I've written this in assembly, so that doesn't call anything. It will just decrement the value, and then if it notices the ref count has reached 0, it will actually free the object. So that's our cleanup, I guess, at the end, which is to load left, which was the PyObject pointer, decrement the reference, and load right and decrement the reference. So the value stack going in should have 2 objects, left and right, and going out it should have the result. So I know that, just make a note for myself, emit the result, which should be pi true or pi false. Now the next step that I want to do is extract the object fval for left and extract the same for right, and make sure I get this the right way around as well, because also this is going to move outside of the switch statement because this code will be the same. So let's do that now, because otherwise I'll forget. Because it's just the branching that's going to be different. And I'll show you how that works in a second. So the way that, because the way we do the comparison of the values is as a branch operation, which is how you would do it in assembly as well. So you'd branch if greater than, and then you'd branch to something which returns false. Otherwise, you'd fall through to a branch which says return true. So first step would be to extract the value for left. Because left has been popped from the stack, we actually need to load it back onto the stack again. So I'll first load that local for left. I might figure out that I didn't mean to, you know what, actually this is generic, so let's put this at the top as well, just to make these different cases easier. Okay, so omit the left hand side value, and then what I want to do is basically load the field. There's a macro to do that, which takes a type and then takes the name of the field, which is that. So what that will do, once my computer catches up, is it will load the, does an indirect load, which is LDI. So it will load the offset of the, for PyFlow object, it will load the offset of the ob fval field. So the offset basically is how many bytes, if left is at memory address X, how many bytes beyond that would the ob f value be? And because that's a fixed number, like this is a struct in C, so PyFlow object is a struct, so this double will actually be at a fixed address beyond the pointer to this object. So we know that for certain, which is why PyFlow object has those macros for get the float value of this, like PyFloat as double is a macro because that it knows the address. The C compiler makes that easy for you. You just reference it using these arrows, but we don't have that luxury because we're writing assembly code. So we can there's a macro here that we've written that was originally in Pyjion actually before I joined the project, but it's used really heavily. So what that will say is assume that there is a pointer on the stack, then add to that pointer address, add the offset of that field, and then load the value. So now we will have loaded onto the stack the object. We'll have popped that object as a pointer off the stack. we'll have loaded the memory address of the value, and then we have the value on the stack. So at this point, the value stack should basically be the number 1.5 or the float value. So that now exists on the stack. We'll leave it there because when we do the comparison, we need two values on the stack when we do the comparison. So we'll do exactly the same thing, load local write, and then we'll do the same thing there. So now on the top of the stack, we have the right-hand value as a float, and on the second value on the stack, we have the left-hand value as a float. So now what we're going to need to do is do a branch operation, which I'm going to need to think about. So the way that branch operations work in the JIT is that you have you essentially create labels because assembly is sequential, and if you're just writing assembly, you'd have essentially a go-to statement which you'd branch to a label in assembly. Now we're not actually writing assembly at this point, we're writing SIL, but SIL does have, just as it does with, it's got a concept of labels as well. So I'm doing one called it's actually been a couple of weeks since I've used this. Just emit define label is the right syntax. Yep. Okay, so we're going to have one for is true, and I'm going to recycle the branches for true and false, right? Return true and false for the different cases, and then just emit a different comparison branch for each one. I'll show you what I mean in a second. So if you want to emit greater than operation, the SIL code we were looking at was branch greater than. So branch greater than value 2, value 1. I'm going to check the order in a second, like I said, because I'm probably going to get it wrong. No, that is in, no, it's branch. And then there are lots of different branch types. So we just made that an enum actually, just to make it simple. So branch greater than is the enum, and then when you call that function, it will actually emit the right SIL code automatically. So branch greater than, and then I want to jump to the is true branch. And then I need to work this out. Let's deal with that. Let's deal with the is true branch first. And the way you do that is, what does it think I've done wrong? Come on, catch up. Yeah, that's fine. Okay, so what we can do now is we can mark the label. So, is it emit marked label? Yep, is true. So if it will have popped the values off the stack, right hand side, left hand side. Let me just check this is right. So the top would be right. So value 2 would be the right and value 1 would be the left. So saying is value 1 greater than value 2, which should be the right order, I think now. Okay, so now mark labels that would jump basically to this block. And I just nest these just to make it simple for me, but basically can then emit true, which I thought I'd done. Did I? I'm sure I've done this already, so let's just. Oh, apparently not. Okay, so right. And I need a second label because I need to jump over, so this is emit true. We're then going to have a second label which would do like emit false. But the way it is now, like it would jump to this branch and then it would continue, it would emit true and then it would emit false. Like that doesn't make any sense. So the best way to do that is basically to have a branch, like an exit branch. And then at the end of this, then say branch always, which would equate to a jump statement in assembly, free and exit. So what that'll do is then say it emit the true object, duplicate the pointer because we also want to increment the reference to true, which is something that you saw when it did pi bool from long, like that's how that works. And then jump over this branch case here and then continue down. So I then need another label for free and exit. And then I need a label for is false because I'm going to end up referring to that a few times in the future as well. Forgotten how to type. Okay. Okay, so if this branch does not, so if it's not greater than, then we're going to jump to the false branch. So we then do a branch here, which would be branch always, which is a jump statement to is false. So this is a conditional branch. So say if left is greater than right, jump to is true, which is this block here, which then says emit a pointer to true, duplicate that and then increment the reference. Then emit a branch to jump to here. If it's not true, i.e. it's not greater than, then jump to the is false label, which I haven't defined yet, so I'll put it in here. The nesting does nothing other than just help with readability, hopefully. I don't need a branch always to free and exit because it's the next instruction anyway, so I'll just let it fall through to the next instruction. So it now should be easy, I guess, relatively easy to implement the other operations. So we've got EQ, we've got pi NE not equal to, we've got case pi greater than equal, we've got less than equal, and we've got less than. I think those are all of them. Let me just double check. Or 6. Yeah, the 6 operations. Okay. So this should be relatively straightforward now to implement, I think. Equals should just be branch equals. Not equal should be branch not equal. Greater than equals is branch greater than equal. The unsigned version is just to do with signed and unsigned integers, which we don't have to worry about because this is a double. So it should natively know that anyway. Less than equal, and then we've got branch less than as well. That all seems to make sense to me. And then that's finished. Okay, so if they're both floats, then do emit compare floats. Let's compile it and see what happens. Okay, let's run the tests and see if this crashes. I don't expect this to work first time, for the record. No, I didn't think so. All right, what's going on? Oh, I also did something else, didn't I? I was working on upgrading the .NET compiler to, yeah, I thought this might crash. Working on upgrading the .NET compiler to .NET 6 preview. So this is actually crashing for something completely unrelated to what we're working on. Instead of running all the tests as well, I'm just going to have a really simple, just to test exactly what it is I want to, I'm looking for here. So let's, sorry, Pyjion has a lot of tests. Let's see if that works, because that's the most basic test I can think of. So this, the test classes in Pyjion will, like create a sort of mini Python interpreter and then just test Pyjion with that string. So it will define the function X and run the function and then assert the output. Why is it running completely unrelated code? That's not what I said, is it? Test boundary ranges. Come on. Yeah, that's going to be interesting. So, yeah, that's failing, but that's really going to test it. I think if I thought my code was going to test it, that's really going to push it. Let's see what it does. Okay, so it's It's not actually telling me the output because I'm in release, not in debug. Let's change the configuration quickly, and then I'll. So instead of using the source version, I'm going to use the compiled version of .NET. Am I broken? I don't know if the streams. So the most likely reason for this to fail is that the .NET compiler is very particular about stacks. So if you if the size of the stack is different from the entry point and the exit point of a block, then it will just won't compile. It will just say you've done something wrong. So the tests, most of the tests test a number of things. They test that the stack effect basically of every block is equal. So why I reckon this is failing is because it's complaining because there's either too many values or not enough values on the stack for that operation, and I've done something stupid. So let's see what it says. No. What's the problem? Failed to compile. I'm trying to remember what that means. I'm pretty sure it is the stack effect is wrong. So I must have done something stupid. I'd say this wouldn't work first time. Let me just think about this. So I just said this in chat. I now know what you mean. Okay. Yep. Nice spot. That is a typo indeed. Is true branch skip false exit? Is false branch true? Is false exit? Okay. I'm interested to see if this is going to work. Hey, it works. I am surprised. I'm very surprised. Okay, that's interesting. It just seems to work. That's cool. Let's run all the tests. All the tests are passing, except the ones that I've marked as known failures, which are there's 25 there. That's awesome. Okay, so final thing, I guess, is that there's one case that I haven't considered yet. So this is when the left-hand side and the right-hand side are known types. Now that is, in the case that I'm running in the test, it's easy because it knows that it's a float and that is a float. In the floating point numbers in the benchmark, it doesn't know what self.x is or other.x is. Yeah, it's got no idea. Because it could be anything. I know that they are floats, but there's nothing to stop you to assigning them as strings or an instance of a class or anything. Like it really doesn't, affect it in that way. So the way that Pyjion is recently doing this, so the feature that I'm working on is this thing called profile guided compilation, and the two stages that I talked about earlier, the abstract, basically building like an abstract version of the stack which just has types, and then using that as a way of being a bit smarter, I guess, with what we do on the compilation phase. So this function is going to run, that function in the load test is going to run 100,000 times, I think, at least. So, and each time it's a floating point number. Now, the principle behind profile guided compilation, I'll just refer to it as PGC. The idea is simple, and it's based on profile guided optimization, which is not a new thing. The principle is that you observe what's happening on execution, and then you assume that if it happens like that, then can we optimize the path most frequently occurring? So what does that mean? It means that in the test float benchmark, self.x is always a float. Other.x is always a float. So let's treat it as a float. However, this is Python, it's dynamic. It don't compile it as a float, because if you change it to a different type, it will just segfault. Like, it will just try and calculate the field offset of some other type, and it will just crash completely. So what I've done with PGC is that these abstract values on the stack will actually have another flag. So PGC will basically run two stages of compilation. It will run an initial stage, which is called a profiler, and it will run it'll basically emit all the code to execute the function properly. But it also emits these probes, which will basically say, okay, what types are currently in the stack? What are we interested in? And then you can then use those probes the second time. So it basically compiles the function twice. And because it's a JIT, it compiles it the first time you run it, and then the second time you run it, it will recompile the function. So in the case of the compare operation, it doesn't do profiles for everything at the moment. I've only put them in for certain operations. So what I can do let me just make a branch before apparently I've already started working on that, but I don't remember that. Must have been a dream. Is when I'm doing the initial phase to work out, when I'm building the abstract stack, what I can do is make an assertion that PGC is ready, and then remember PGC update stack, and I want two positions. I want the top and the second. I think there's one other thing, probe. That's it. So what I'll do is, so currently this optimization that I've written would only work if it knows 100% what the types are, which is unlikely because unless you've defined them as constants, it's not going to know what the types of the values are. So in this case, what it will do is whenever it has a compare operation on the first compilation phase, it will emit probes for the top two stack values, and it will save them in a profile in the code object. So the code object basically has an extra field which has got some information about what's going on. It does that by calling where is it? It recalls capture PGC stack value with the profile data, and then it records the opcode position, the stack position, and the value. And then for that, we then say increment the reference to the type and increment the reference to the value, because we're going to use them in future, and we're going to refer to them later in the compilation. And abstract values will then we can then assert what type they are. Now, because they're changeable, we also want to be really careful about this. So what I can do here is just make a flag for this function, emit compare floats, which is gonna put a type guard in. So if I go back to the definitions, okay. I'll explain what this means in a second, but I know that left-hand side value has a needs guard, or the right-hand side needs a guard. It means that if the type of the left-hand side value or the right-hand side value, if that type has been asserted based on profiling data, then don't, it's changeable. So don't go nuts with the optimizations, because if I ship this feature, and you called the function and it was using floats to do this comparison the first time, and then the second time it was using integers, like this would just explode. So what we need to do is, if we're getting the type information, if we think that it's a float based on type information coming from the profiler, then we should emit an additional set of instructions which guards against the type changing to something else. So what that means is, if we need to basically add some extra instructions here before we do this code, and I think we'll do it for everything. How would I work this? Let me just think about this. So because that emits the generic version. That's not cyclical, is it? It's not. No, it's not. Okay, so we also need to work out the stack effect, which is going to be the complicated bit. Okay, so don't define the... Oh, this is complicated. Okay, don't push them onto this. Don't pop the values yet. So if we need a guard, then first thing we should do is, can we do it this way? Let me actually do pop them off the stack and onto locals because I want to assert the types. So at this point I want to just assert that the right hand side is a float and that the left hand side is a float as well. Otherwise the code is going to fail spectacularly. So again, we can load the field, and that would just be a Py object because the type is type, I think. So that now pushes the pointer to the type object onto the stack. The type objects are recycled. So the float type is an object pointer, which is not heap allocated, so it belongs to the interpreter, so it's going to go away. Also, we incremented a reference to it, so that pointer shouldn't disappear. So what I can then do is emit the pointer to Py float object type, which I need to do as the address to it, I think. pyfloat type, is that right? Okay, so emit the address, the pyfloat type, and then we've got the type of this object on the stack, and then we do a branch, branch not equal, and then we would do guard fail, and then I do the same thing for the I don't know why I've done it that way around, but never mind. It doesn't really matter. So guard fail now needs to be a label that I define. And then what I then need to do is to say, okay, if it's not a float, then jump to some code which skips over all of this, because that's the stuff that's going to break, right? So where do I need to jump out to? Probably the bottom, I think. And then again do a guard break, which is going to do emit mark label guard fail, and then if the types have changed, then I need to just do the generic version, which is so I'll load I4. Oops. Let me just remember what the actual. I'll just run that function. It's easier instead of repeating myself. Okay, so, and then I've got the comparison type. Okay, so if there was a guard then, and the label was here, now we need to check the branching for when the guard doesn't fail. So when the guard passes, what would happen? So it would execute the code to this point. Then I need to basically have a label here that it would jump to, which would be guard pass, I guess. Which is just I guess the point that you jump over. So mal.branch always, and then guard pass. So I'll explain in a second how this is working. Okay, so if it requires a guard, load the right-hand type, get the comparison to a float. If it's not a float, then jump to guard fail. Do the same with this one. So if it is a float, and if that is also a float, it will fall through to this code, which would then load the locals. It would it would load the left and the right. It would do our optimized version, and it would then get down to this line which says, okay, we've now executed all that code, jump over this block into this block, which would just fall through to the end of the code. Then if it failed, then it would jump to here and it would run that function, which would call the generic method, which would look up the type slots. So I believe that should have the same stack effect that the previous. So I guess the final thing we can do is run the float benchmark against the release profile at all, because this is really gonna, this should test the profile and the optimizations, and it should recompile it the second time around with this guard and the optimized comparison. The thing I don't know is how much of an impact it'll have, because that, I don't know, like these lines, this function, like how much of the overall computational time is made up of this function. But yeah, it should make some difference, I guess, because it's going to run it a lot. So we'd hope that it would make a bit of a difference. Well, I reckon it's slower. Of course it does. Yeah, a number of different things going on here that I need to look into. But one is I've got a ton of stuff running in the background. Second, I need to run PGC over the code. No, not PGC. I need to run PGO over the code, which I do by running and then recompiling the profile data. So CLang, you can basically give it profile, like runtime profiles, and it will recompile the C code to be much more efficient. I also haven't written any tests to assert that this optimization is even kicking in. So yeah, that will be something that I probably have to do next, but I'm running out of speech and yeah, I need a break. So I'm going to stop the stream, but if anyone found this interesting or has any questions, then yeah, please just let me know on whichever forum, and yeah, I'll open a PR for this, and then I'll probably share later on Twitter and stuff, like whether this made any dent on the benchmark.